Petrology, the study of igneous rock. What is an igneous rock? It is a type of rock that directly crystallizes from the magma. The rock that directly crystallizes from the magma, that is called as an igneous rock. So during cooling of the magma, so rock can be formed below surface or above the surface. So magma can consolidate below the earth or above the earth. So that's why we can simply classify them as intrusive and extrusive. According to the place where they are solidifying. So this is a primary rock directly crystallizes from the magma. So what is a magma then? So magma is a molten material, so like that formed by the partial melting of lithospheric plate or mantle material. That is formed by the partial melting of lithospheric plate or you can say mantle material. So due to the partial melting of lithospheric plate or mantle material, but why we don't get magma in all part of the earth? May technology part of the earth you will not find magma. Why? What is the reason? There are specific places where magma will form and will get volcano or something. So, as we are saying, partial melting. So, for melting, the substance should reach to its melting temperature. So, when it will reach to its melting temperature, then it will melt. So, lithospheric plate or mantle, those are heterogeneous substance. So, they will not melt at once; they will partially melt. So, those components or those constituents which will attain their melting temperature, they will melt and form some magma. So, that magma that is called as primary magma. Then, when it will rise upward, it will be evolved. But why will not get magma in all part of the earth? Suppose you are standing on a crust, below there will be mantle. Why there is no magma within the mantle? What is the reason? In a normal crustal region, the if you go down, the heat will increase only by geothermal gradient. So at upper crustal level, the geothermal gradient is your up to 25 to 30 degree per kilometer we are considering. So this is suppose the geothermal that will increase with depth. So material that will melt will below the you can say the lithospheric slab that is your petrotite, or you can olivine material. So the geotherm is not that much or sufficient to melt the petrotite or material that when partially melted to form magma. So this is the solidus. This is you consider depth. If you consider melting temperature. So at this much of depth, temperature required for melting is this much. But due to geothermal gradient, the temperature is this much. That's why in the normal crustal region, lithospheric fluid or mantle metal is not melting. The geotherm is not sufficient to melt the material. And there are also radioactive heat that is also not sufficient to increase the geotherm. So if in any places two conditions will happen. One, either the temperature will increase to the solidus, otherwise the solidus, that is the melting temperature of substances, that will decrease to the zero. The two things will happen. What thing goes na? Agar mera geotherm will increase to solidus or solidus decrease to geotherm. There are two conditions where geotherm will intersect the solidus. So when geotherm will intersect the solidus, that means ki the temperature is sufficient for melting. So that's why we will not get magma in all places of Earth, because geotherm is solely, it is not sufficient to provide that much of solidus temperature of the subsurface of Earth. The normal cross situation where geotherm is not alone sufficient to melt the material, so it will not intersecting the solidus. So there are two conditions we are seeing here. One, either geotherm is increasing to intersect the solidus here and here, and here the solidus is decreasing to intersect the geotherm. So these are the conditions where magma will generate. So there are places mid-oceanic ridge, we will consider hotspot, and subduction zone. First we will consider mid-oceanic ridge, what will happen at mid-oceanic ridge. So this is our plate. Below that, there are convection current. So the hotter material will present here, so they will gradually move upward. Then during their upward movement, they will lose heat because of the slow movement, and when it will reach here, they will become colder, and again they will descend down when they will cool down. Then during descending, they will again gain heat. Then hotter. Then this is the condition where the convection current is going up. So अगर plate will break, if plate will break, because plate is it is pressurizing the mantle region. It is pressurizing the mantle region. Due to convection current, there will be no change in the geotherm here, because when this hotter magma they are reaching in the shallower region, they are losing heat. That's why they cannot contribute to change the temperature here or to change the geothermal. नहीं ये ठीक पहुंच लेवल को कहाँ जाऊँ cooler ହେଇଯାଉଛି. So if any cases, if anything happens when this lower portion of the magma suddenly rises to this portion without losing heat. well then, अगर ये यहाँ तक आ जाएगा without losing heat, so that means कि the temperature of this portion will increase. Temperature of this portion will increase. Then how that will happen? Because of breaking of this plate. So if you are pressurizing something, okay, to release the pressure, then the material will suddenly rise. ଯଦି ପ୍ରେସରାଇଜ କରୁଛ କିଛି ବ୍ରେକ୍ ହେଇଯାଉଛି ତାହେଲେ କ'ଣ ଏନିଥିଙ୍ଗ ବିଲୋ that will rise suddenly. Not about time because कि ताको sufficient time मिललानी to lose the heat. So that's why suppose कि you are taking something hotter thing, if you go slow then it will lose heat. If you go fast then it will remain hotter. So ଏଠୁ ଧର ତୁମର magma ଯେତେବେଳେ rise କରୁଛି, so it is now hotter here when it is rising through a convection current, so it is rising slowly. So slowly rise कर रहा है तो it will lose heat. It will lose heat. But if the plate will break, then it will suddenly rise. So the plate is pressurizing the mantle region. So when it will break, the lower part of the magma, they will rise suddenly. So without losing heat, that is called an adiabatic condition. That is called adiabatic condition, where it will not lose any heat. That is called as your decompression, because the plate is breaking means it is releasing the pressure. That is also decompression. So for this, the geotherm of this region will increase. Geotherm of this region will increase. Now it is sufficient to melt the lithospheric plate here and will generate magma, and gradually the fracture will widen and magma will to the surface to form volcano. So it is here this type of melting is called as a decompressional melting. Understood? So this condition is represented here. So before the breaking of the plate, the geotherms are like this. Okay. So when the plate will break, the geotherm will rise here because of sudden rise of the lower material. So you can see in this figure also at shallower level, where in normal cross geotherm is like this, in mid-ocean is very high. So now the geotherm will increase and it will intersect and magma will produce here and that will give volcano. This is in case of mid-oceanic region where the geothermal will increase. There are another places also where geotherm will increase but gradually. That is in case of your hotspot region. So where continuously magma will rise from the hotspot region and it will reside here. It will rest here. So all the heat within the magma, it will be scattered through the continental crust or in oceanic crust. So due to multiple intrusion, or you can say continuous rise of the magma, the geotherm of this region will increase gradually. Okay, it will increase gradually, and with a sufficient time, this place, the temperature of this place will increase that much to touch the solidus, and melting will start. Then when the melting will start, this thing will become thinner, and volcanism will occur. What happens usually in hotspot region? If any plates that above the hotspot region, that means it will always form a volcano. So this process is also called as magmatic underplating. Similar thing happens at divergent plate boundary, sorry, at convergent plate boundary, where the plate will melt and it will rise upward, this continental part or oceanic part. So due to continuous supply of magma, the temperature of this portion will gradually increase and it will touch the solidus and it can give volcano. So these are two places where the geothermal is gradually rising or gradually increasing and it will touch the solidus and there will be volcano or generation of magma. This is called increase in temperature, where the temperature is increasing due to, let's say, multiple intrusive event or continuous supply of magma, where the magma will underplate or magma will reach under a plate. That's why it is called as a magmatic underplating. But in case of subduction zone, the solidus will decrease. It is because one thing, if you add water to something, then its melting temperature will decrease. This is the principle. The addition of water decrease the melting temperature. So if you add water, the melting temperature will decrease. That's happening in case of subduction zone, where the diving plate, the subducted plate, will produce water by dehydration reaction, or any it is oceanic plate, so it has hydrated mineral. So due to dehydration, it will release water. So due to the addition of water by dehydration reaction, the melting temperature of the lithosphere slab will decrease and it will intersect the geothermal, that region. So here there is nothing that will increase the geothermal. Here the solidus is decreasing because of addition of water. So it is solidus decrease. So this is because it decrease addition of water, or you can say volatile addition, or you can say this is also called as flux melting. समझे? This is called as flux melting. So there are three cases. In one case, geothermal is suddenly rising. Another case, geothermal is gradually rising, and the third case is the solidus is decreasing. In all cases, the primary thing, the solidus must intersect the geothermal to generate magma or to start a melting of the plate. So these are the three processes how magma is generated. Understood? को समझ में आया? डाउट हो तो पूछ सकते हो. So magma can be of three types depending upon which material is melting, so or how it is evolving. So it is basaltic, andesitic, rhyolitic, or you can say basaltic, intermediate, acidic. So it is classified on the basis of silica percentage. SiO2 percentage greater than 65%, it is acidic magma. So if andesitic magma, it has no 55 to 65%, intermediate, and SiO2 percentage is 45 to 55, it is basaltic. If it is less than 45, it is ultrabasic. These are the major elemental content. The gravitic magma has more potassium, sodium, and silicon, and basaltic magma has more of iron, magnesium, and calcium. Volatile content, mostly you'll find H2O. So among all the volatiles, 90 to 95% is your water vapor or steam or H2O, what you can say, and then carbon dioxide. Then other constituent at very little amount: carbon monoxide, sulfur, chlorine, H2S, SO4, HCl, anything. Then temperature. So temperature in magma, where the acidic magma has highest temperature. Oh, acidic magma has the lowest temperature. Basic magma has the highest temperature. Where you can say basic magma ranges between 1000 to 1200 degrees centigrade. Then acidic magma is 650 to 800 or 700 to 800 degrees centigrade. Then andesitic magma is 800 to 1000 degrees centigrade. They are not specific. You can write down 600 to 700 or like that. The range. Then comes to viscosity. So temperature for it, when if you increase pressure, the melting temperature will rise. So that means कि pressure is directly proportional to the melting temperature. So it is another characteristic of magma where if you put a magma or a magma is forming at a very greater depth, it will have higher temperature that it is forming at the shallower level or at the surface level. So that and the volatile content is also affect the temperature of the magma. So if you are considering a dry magma, it will be higher temperature than the wet magma. These are something that helps to know the temperature of the magma. So the constituent within the magma, the crystals or the other constituent, they can help to know the temperature of the magma. But always remember the constituent always he give the information about its crystallizing temperature, not the temperature of the magma. Other studies, the isotopic studies or trace element studies, where you can know the temperature of the magma. Then also viscosity. So viscosity is the resistance of flow. So viscosity it can be calculated by shear stress by rate of shear strain. So how viscosity affect the magma? Viscosity it will affect the rate of placement of the magma because if it is a high viscous magma, then its mobility will be less. If it is less viscous magma, its mobility will be more. Then shape of the igneous body that depends upon the different type of form or structures are formed due to more viscosity, like laccolith, fraccolith. Those are the type of that depends upon the viscosity. And sinking and floating of crystal that change the bulk composition. If there will be more formation of crystal, that will increase the viscosity. So if there is a, you can say, a recharge of magma, then viscosity will decrease. Magma mobility and development of universal crystal. Because if you have a very less viscous magma, there will be more diffusion of ions. So if more diffusion of ions, then universal crystal will form. If you have more viscous magma, then there will be less diffusion of ions. So it will produce a तुम्हारा कौन कहते हैं anhydral crystal. So well developed crystal because of low viscosity. ଯଦି low viscosity ହେବ ତାହେଲେ କ'ଣ mobility ଅଧିକ ରହିବ. So mobility ଅଧିକ ରହିଲେ you will form a universal crystal because the ion can diffuse or ion can migrate to the nucleation side. If it is a the viscosity is higher, if the viscosity is higher, then more ion cannot mobile through the liquid or through the magma. So that will produce an anhydral crystal. So most magma tomorrow they will behave like Newtonian fluid where tomorrow shear stress and tomorrow rate of shear they have a linear relationship like this. Most of the magma. But in some kind, due to crystallization, the percentage of crystal will increase. When crystallization will occur, the percentage of crystal will increase. So suppose you think of water. So water can easily move. But if you have a very denser material, if you apply force, it will resist sometimes, then it will flow. If बेसी denser material थिबो fast किसी time पर्यंत resist करें, then it will start to flow. So that means कि some yield stress is required for the movement of the fluid. So if the crystal content will increase, that will happen. If the crystal content will increase, it will become more dense. So when it will more dense, it will more viscous, and if we are applying force, it will require some yield strength to start the movement or to be in mobile condition. So like this. So up to this much of shear stress, there will no rate of shear. Up to this much of shear stress, there will be no rate of shear. So it is that condition where we are applying stress, but there is no shear stress. So each time if you want stress apply if I applying stress here to this much extent, we are not getting any shear strength. That means that thing is not responding to the force, not getting any rate of shear. So the formula is viscosity. It is shear stress by rate of shear. So if rate of shear is 0, then viscosity will be shear stress by rate of shear. If rate of shear are considering 0, then viscosity will be infinite. Rate of shear will be infinite. So as the percentage of the crystal will increase, then fluid will require some amount of yield stress to be in motion. Okay. So thus, in that condition, at lower stress, magma appears to have infinite viscosity. Because of this. After that, it will have a linear relationship with the shear stress and shear stress. Once it will overcome its yield strength, then it will have a linear relationship with the shear stress and rate of shear and shear stress. If the crystal percentage increase to extent, that is your 60%, then same thing will happen. At lower stress, it will be infinite. That condition is known as your Einstein limit, where the percentage of crystal is 60% within a magma. So magma is suppose crystallizing, the percentage of crystal is increasing. Now we have 60% of crystal and 40% of melt. So in that condition, it will behave as a solid. So it has 40% of liquid, but it will behave as a solid. And in nature, if I consider magma, then actually it will behave like linear, or you can say Newtonian fluid for sometimes. Then at higher stress, it will be again non-Newtonian fluid. It will behave like non-Newtonian fluid. Suppose at lower stress, this line is straight. Now it is curving here. Curve. This curve means they are not. They doesn't have a linear relationship at higher stress, but at lower stress they have a linear relationship. So this condition is called as your pseudoplastic behavior. So they are at lower stress. They are at lower stress. They are having a linear relationship, but at higher stress they are having a non-linear relationship. this is called as a pseudoplastic. They are not perfectly Newtonian fluid. During what a magma which doesn't have any crystal. It is simply a magma. It is not perfectly behaved like a non Newtonian fluid, which it has a linear relationship always. It will behave like a pseudoplastic. That means it has a linear relationship at a lower stress level, and at higher stress it will behave like non-Newtonian fluid. So, what are the different factors that control the viscosity of the magma? Uh, First thing, temperature. When temperature will increase, viscosity will decrease. When silica percentage will increase, viscosity will increase because silica percentage or more, SiO polymerization we can say, or ALO polymerization, because of their increase in linkage, the viscosity will increase. That's why you can consider Bowen's reaction series where olivine is not having isolated tetrahedral, but quartz having tectosilicate where all the oxygens are shared by other tetrahedrals. So that from olivine to quartz linking of oxygen with other tetrahedrals are increasing, and that will indicate also viscosity is increasing. Olivine, then you will get pyroxene, single chain, then amphibold, double chain, and so on, tectosilicate. Then addition of more volatile matter, it also decrease. So viscosity has an inverse relationship with temperature and volatile matter. It has a direct relationship with the cilia content. The cilia content will, when increase, the viscosity magma will increase. So these are the different characteristics of the magma: viscosity, temperature, then how pressure will affect the magma. Suppose कि at this depth magma is forming due to partial melting, so that may be increasing temperature or decreasing pressure or flux melting. Then after formation it will rise upward because in newly formed magma are hotter and less denser. So it will rise to the lithospheric column towards the surface. So when it will rising to the surface, the depth will decrease. The depth will decrease. When the depth will decrease, the temperature will decrease. So when the temperature will decrease, that means this rising magma will start to solidifying. धीरे-धीरे it will start to solidify. So during solidification or during cooling, by some process, it can develop a well-developed crystal, or it may develop a anhedral crystal. So what are the different conditions that controls the cooling behavior of magma that we will study here? So these are all the causes of igneous texture. These are all the causes of igneous texture. So during for ascent of magma to the surface, these three things will control the crystallization of crystal. First, initial nucleation of the crystal. First, there will be a nucleation. Then, that nucleation should fade by other ions so that it will grow. Crystal will grow, and for growth, ion must diffuse to the nucleation center, and also there should be the availability of ions, because if there is no ion, they will not diffuse to the nucleation center. So that it should be availability of ion within the magma, and there will be other condition which will helps to form a well developed crystal and the growth of the crystal. सेमती कंडीशन दरकार जोथरे कि तुमर कण कूलिंग टाइम रे that certain condition which will favor for the formation of a larger crystal. There are a combination of factors. So first we'll discuss what is nucleation. What is nucleation? We'll discuss that. So what is nucleation? So nucleation is the process where clustering of iron will start. There are some site within the magma where iron will start to cluster. First one, they will cluster, they will form a pattern starting of the embryo of a crystal. What? Embryonic crystal. So nucleation will occur at different site where simple we can say clustering of iron will happen. So nucleation is the initial process. Then that cluster cause a partition of iron produce a very small size crystal, what we call embryonic crystal. So it is कि before the formation of the proper crystal, a small size of embryonic cluster will form, that is called as a crystal nucleus. That is called as crystal nucleus. Hmm? এটা পরে it will develop into a crystal. This is crystal nucleus. That means suppose a substance has a crystallization temperature of suppose 600 degree. A melt has a crystallization temperature 600 degree. So when it will reach to 600 degree, when it will reach to 600 degree, it will start to crystallize. It will start to crystallize. So 600 degree, when it will reach, these things will first happen. The site will create, clustering will happen. Then that cluster, that embryo will develop into a crystal. But the temperature is slowly decreasing. If the temperature is slowly decreasing, that means ki 600 to less it. That means ki suppose it is at 590 or 580. Up to that the temperature, you will not get any crystal. You will not get any crystal. Example those suppose ki if we are considering eutectic. Okay, if we are considering eutectic, तो eutectic मना समझता होता. Suppose this is a eutectic thing, two components here. So this is a liquid. So what we are saying, if this is a liquid, then it will start to crystallize here. Start to crystallize here, but we cannot calculate the percentage of solid here. If we are saying the crystallization is starting here, then that must be some solid. But here we cannot calculate because it is showing it is 100% liquid. If the liquid is here, then we can calculate that this much amount is solid, this much amount is liquid. Understood? So when any melt that touches its melting temperature, but these things will start clustering, then embryonic crystal, then it will develop to a well developed crystal. That depends upon its supercooling or undercooling. Up to that much temperature, when it will touch its melting temperature to the development of the crystal, proper crystal, that cooling will not get any crystal. That's why it is called as the when a liquid is cooling below its melting temperature without forming solid. That is your supercooling or undercooling. So those clusters will form, they will always not stable. Cluster is also always not stable. There are many nucleation site will clear, but they will not stable. There should be sufficient internal volume of fully bonded ions to overcome the surface related instability. There must be that much of force within them and that much of volume so that it can remain stable. The site can remain stable so that other ion can add to the site. So this nucleation process, where the clustering will start to the development of a well-developed crystal, that is your undercooling. That is your undercooling. So this is your, because of the stability you require some degree of undercooling. What is a cooling of melt below the true crystallization temperature of a mineral? Below the true crystallization temperature of a mineral, or you can see it is super cooling. Now you think whether a well-developed crystal will form in higher degree of undercooling. If there will be more undercooling, it will form a well-developed crystal, or less undercooling will form a well-developed crystal. More undercooling will form a well-developed crystal. A less undercooling form a well-developed crystal. Bravo. Right. You think about this and answer me in the next class. Whether low undercooling will produce well-developed crystal, or higher undercooling will produce well-developed crystal. With causes. So there are also different structures or different minerals. They will nucleate at different rate depending upon their structure. So those having simpler structure, they tend to nucleate more easily. If something is nucleating more easily, it will produce smaller crystal. Okay. Those with more complex structure, they will produce. They will nucleate. Their nucleation will be difficult, but they can produce larger crystal. So, example, you can say more oxides such as more magnetite or ilmenite. Generally, they will nucleate more easily with less undercooling than does olivine, followed by pyroxene, plagioclase, and alkyl feldspar will progressively more complex SI collection. So it means that's why more oxides typically smaller and numerous, where alkali feldspar generally go quite larger regardless of degrees of undercooling. The thing which is when anything that nucleate more easily, there will be more nucleation. There will be more nucleation site. So that means if you have more nucleation site, then it will develop a smaller crystal because there will be less ion availability. But something is nucleating, the nucleation is more difficult, it will produce lesser nucleation site. So if lesser nucleation site, they can grow to a larger crystal because if two conditions will happen. One is ion availability and space. Nucleation, if more nucleation, less space will be available, and if less nucleation, less nucleation, more space will be available, and more ion also available for each nucleation site. So after nucleation, clustering, after that the nucleation will form, then it will form a will develop crystal. Now the crystal will grow. Now the crystal will grow by addition of ion with its faces. The crystal faces, ion will add and crystal will grow. So where तुम्हारा existing crystal will become larger by addition of ion to its crystal lattice, but it will not grow in equally in all direction. So sometimes it can grow equal in all direction, or sometimes it will grow more in one direction than other direction. That's why it will get different shape of crystal. So different phases can grow at different rates. So like the faster growing phases tend to have smaller interplanar lattice spacing. That means higher surface energy. So if there is smaller interplanar lattice spacing, that means there will be more stability here. On that phase, there will be more stability, so that it can attract the ion more easily. So any ion, any more lattice with small lattice spacing, they will have a kind of greater or stronger bond, so that anything will add here can be stable here. So that's why to take it more, where the smaller interplanar lattice spacing, that surface is called as your having higher surface energy, having higher surface energy. So any ion that will add here, it will be stable here. So that this space, this phase which have a very smaller interplanar lattice spacing will grow faster than having a greater lattice spacing. Where they have low surface energy. Then more crystals or ions would have produced way. So ion they will fall into the lattice position. So ions are from the solid spheres. They should fall into the lattice position, form a well developed crystal. Sometimes what happens they doesn't fall in the lattice position where the crystal defects are occur. Because once they are falling into a position, they cannot change their position. So during the growth of the crystal, that's why you will get crystal defect or other thing like cleavages or other thing that will form during crystal growth. It is a defect during the growth of the crystal, where the can say ions or the atoms they will not fall into their correct position. Once they will falling any position that is fixed, then during growth iron requires. So, for suppose a face is growing, that means ki iron should diffuse to that face, and should diffuse to that face and will add to the surface. So, during the growth of the mineral, sometimes what happen, the magma or the nearby melt, it will deplete it, the required iron. So, required iron, जहाँ हमारा required था, that gradually depleted within the magma. So, growth to proceed, that must diffusion, because suppose there is a nucleation here, it is growing, so it is using the nearby ion, it is using nearby ion for its growth. Now that start to deplete. Say patakon say kuda sorry work like that. So now there is a deficiency of ion nearby the crystal, so there must be a diffusion, there must be a diffusion of ion to the nucleation site or to the crystal face. So that's why for growth of the crystal, for the formation of a larger crystal, diffusion upon a most important process, which will depend upon the viscosity. If the magma is less viscous, then ion can easily diffuse to the nucleation site, so that it can grow to a larger crystal. If it is more viscous, then it will be difficult, or you can say it cannot be moved or diffuse to the nucleation site. So it cannot grow into a larger crystal. Understood? So it is happen because of the when the composition of the growing crystal is differ from the well. Sometimes the crystal is forming. Suppose ki olivine is forming. Ki Mg, Fe, those ions are required. If there is more availability of calcium, sodium, then gradually the MgF will deplete. So to growth to continue, it must that place must recharge. That place must be filled with magnesium iron by a diffusion process. And another thing, important thing, that is during the formation of the crystal, the melt produces heat that is called the latent heat of crystallization. Latent heat of crystallization. So this heat must able to diffuse away from the crystal, or the temperature of the going surface may become too high for the crystallization process. That means that during the crystallization, that is what we can call as heat of crystallization. So during formation of the crystal, it will also release heat, that is called as heat of crystallization. When bonds are forming, so obvious thing, the heat can be released there. So that heat should be diffused from from that place. So that should be diffused away from that place. Otherwise, the temperature of that place will again increase. So it will start to melt again. So during crystallization, the heat of crystallization always diffuse away from the crystal. So ion will diffuse to the nucleation side and that heat will diffuse. That's the two factors where the diffusion comes into play. So for growth, we required ion, we required diffusion. So all these things are happening in a slow cooling condition. All these things are happening in a slow cooling condition. These things will not happen during one faster cooling because during slow cooling, the sufficient time so that ion can migrate to the nucleation side, then add, then grow. So rate of nucleation, growth, and diffusion. These are three main process. The development of the crystal. So whichever rate is slowest will be the overall rate determining process and exert the most control on the crystallization. So from these three process, which is the slowest one, that will have more impact on the crystal growth. So along with that is slow cooling. So you must consider slow cooling because the slow cooling always produce that initiation, that rate of nucleation, then growth, then diffusion, and also more slow cooling you are calling water cooling. So this is the graph that represent temperature and rate of nucleation. So this is a graph that represents the rate of nucleation and rate of growth with temperature. Rate of nucleation and rate of growth will with temperature. So this is the melting temperature. There you melting temperature. Above this temperature, melt will come. Below this temperature, crystallization will start. So we'll take three reference temperature: TA, TB, and TC. So this is your freezing temperature. This is your freezing temperature. That is where the crystallization will begin. So at the initial stage, up to suppose TA temperature. So the nucleation rate here is very slow. Nucleation rate is very slow at the initial stage due to that slow cooling, water cooling, you can say. In that case, you can see the growth of the crystal is more. Here, you can establish a relationship at the initial stage of crystallization. At the initial stage of crystallization, the rate of nucleation is inversely proportional to the rate of growth or crystal growth. So crystal growth inversely proportional to the rate of nucleation at the initial stage. At the initial stage of the crystallization. Then you consider from TA to TB. First it will increase. Nucleation rate is always increasing like this. Increase. Then again it will start to fall here. Why it will fall? With progressive crystallization, the percentage of crystal will increase, and that will increase the viscosity. Now we'll discuss. Already discussed that. With increasing crystal percentage, the viscosity will increase. So when the viscosity will increase, that will slower the diffusion rate. That will slower the diffusion rate. Now the diffusion rate will control the crystallization. So if diffusion is less, it will not form a well-developed crystal. A crystal will not grow. Crystal will not grow. That is the overall factor that affects the crystallization here. as I was saying, during the growth of the crystal, due to increase in crystal percentage, viscosity will increase. So with progressive crystallization, the growth rate will decrease. The growth rate will decrease, but sometimes at the latter stage or at the end stage of the crystallization, we can get well-developed crystal. Example is your pegmatite, or you can sometimes also get find coarser grain granite. So that is because of the addition of H2O. That is because of addition of H2O. If water will add or volatile matter will add, that will lower the degree of cooling. Sorry, that will lower the degree of viscosity, that will enhance the diffusion. So in that case, it can produce a larger crystal, which will explain the post grain size of pegmatites. Pegmatite form at the end stage of the crystallization. So at the end stage of crystallization, that means that there will be more crystal percentage within the melt. So that meaning it has a higher viscosity, but because of the addition of H2O, that viscosity will decrease and it helps to produce larger crystal. So this is the process that explain how a well-developed crystal, how a larger crystal, how smaller crystals are formed during cooling of a magma. Cooling means when the magma is ascending to the surface. So it will ascend through fracture. Suppose it ascending through smaller fracture, that will ascend slowly. So that will helps to explain the slow cooling. If any case it is rising suddenly from depth to more shallower level, that will explain a sudden cooling. If it is rising more rapidly, that is your rapid cooling. If it is rising very slowly, that is slow cooling. That depends upon how the magma is ascending to the surface. Understood? The IUGS classification, it is about compositional triangle. So I think all know how to read a compositional triangle. So this is a compositional triangle where we take three minerals at the apices. So each having 100% at the apices, and the line parallel, they will be 0%. So from this line to the apices, their percentage increases. Suppose ki x, here x is not, x is 100%, at YZ line it is 0%, then it will increase towards x. Similarly, y here 100% and x line it is 0, then it will increase towards y. It's a compositional triangle. So any point within this triangle will give the will have a composition x, z, and y. So if you replace this x, z, y with mineral, then any point within the triangle will represent a rock. So in IUGS classification, we represent rock with a compositional diagram by taking the major elements. जहाँ पे major composition है by essential minerals. We are taking essential minerals and represent different types of rock in IUGS rock, in case of IUGS classification. In IUGS we use two triangles and combine them. So theta triangle में use करते हैं combine करते हैं. So these are the recalculation. I think you all know about recalculation. समझ जानते हैं ना recalculation part. First, if you are considering any rock, that it consists of different minerals. So the required mineral, what you are required to represent in a composition diagram, you have to choose that much and then recalculate them to 100%. So that thing is, suppose we have x, y, z. X is 9, y is 2.6, z is 1.3. So you have to make that this should be normalized to 100%. So that's why we'll take 9.0, 2.6, 1.3, total 7.5. Then for a 7.5 suppose x value is y and z achi. So you will take normalize. How will normalize? X plus y plus Z. It will give the percentage of X. Similarly, Y by X plus Y plus Z. It will give the percentage of Y. Then similarly Z. Normalize them. Then we will represent in QAP diagram or any triangular diagram. So this is the IUGS classification scheme where we have taken two triangles. One is QAP, another is FAP. One is a QAP triangle and another is FAP triangle. They are joined, so that's why it look like this. So together we can say QAPF diagram. So that Q is quartz, A is alkali feldspar, P is plagioclase feldspar, and F is feldspar or you can say mafic minerals. So why we are taking two triangles here? You will not find any rock where quartz and feldspar are together present. That is the thing. They cannot occur together in nature. That's why you have to represent them in separate diagram. So any rock that contain quartz, it will not contain feldspar. So that's why we have to consider two triangles. One is QAP triangle, one is FAP triangles. That means the quartz will never present in feldspar field, and feldspar field you will never find quartz. But alkyl feldspar and plagioclase feldspar, they are common for both. So they can be found where quartz is found in rock and also feldspar field is found. So mostly in QAP diagram, it is divided into these three main components. You can say one is granite, one is granodiorite, tonalite. So in this case, you can say any rock that doesn't contain a specific amount of any minerals. There is a range of composition. So quartz can occur up to 20 to 60% within a granite. So that's why they are represented within a field. So in the what field represent granite. Then granite has more orthoclase percentage or alkali feldspar content. Then granite has less. Then tonalite has less than 10% of alkali percentage. So that's how we can read the diagram. You already know the cyanite, monzonite, and monzodiorite. The monzonite has equal percentage of plagioclase and alkali feldspar. And this is the drawbacks where diorite, gabbro, anthocite, they are all represented at a plagioclase corner. It is a demerit. It is a disadvantage you can see where it is not properly represented. Its composition is not properly represented within the IUGS diagram. And you have to remember all these things. The total whole diagram you have to remember. So what is the meaning of Q? What is the meaning of A? What is the meaning of P? So you have to लिखे हुए. And this portion during feldspar third presence it will become more dark color, and in this case it will be more lighter color. Just review once the diagram, then we'll proceed. So basically, Bowen series explains what is the sequence of crystal that form from a basic magma. So basic magma when start to crystallize, in what sequence it will start to form crystallize, or in what sequence it will form minerals. First it will form olivine at 1100 degree centigrade, where the crystallization will begin, and it will end at quartz 573 degrees. So in a sequence from 1100 degree it will start to form olivine and plagioclase. Then gradually with decreasing temperature it will proceed in two series. It will proceed in two series. One called as discontinuous series, one called as continuous series. Where more of anorthite and albite, from anorthite to albite, it is a continuous series, it is solid solution series, and here it is discontinuous series where olivine will form, then pyroxene will form, then amphibold will form, then biotite, then mica. Then again, both series will converge here at potassium feldspar, then moscovite, then quartz, then below you can get hydrothermal solution. So in discontinuous series, the olivine crystal that always reacts with the melt to produce the next crystal. The olivine crystal is olivine, it will react with melt to produce pyroxene. That means all the olivine should react with the melt to produce pyroxene. All the pyroxene must react with melt to produce amphibole. So as olivine is reacting with melt to produce pyroxene, so olivine and pyroxene are called as reaction pairs. Reaction pairs. But in case of here, anorthite will form, then it will exchange ion with the magma, then it will form petonite. So here, that's why it is continuous. But here, it is discontinuous because they are reacting from another mineral, that is pyroxene or amphibole. So if you are saying all the olivine will melt with, all the olivine will crystallize, all the olivine will react with SI. Is it true or false? All the olivine, whether all the olivine will react with melt or not? So the reaction will start from olivine crystal and melt. So until unless one of them is consumed, the reaction will proceed. Until unless one of them is consumed, the reaction will proceed. So olivine crystal and SiO2 melt, the olivine crystal will be lesser than the melt. So that's why it will consume. It will consume. But if there is a fractional crystallization happen, then olivine can be found in this level. Otherwise, if there is always a equilibrium crystallization, then olivine will not be found. Olivine only found in case of more fractional crystallization, because if the reaction will proceed, then olivine will all consumed by the melt to form pyroxene. Similarly, fractional crystallization will happen, then pyroxene will get. So this सब जगह react हो सकता है, melt reacting it will forming pyroxene. That means the olivine is not present within the magma. It is all converting to the pyroxene. So how we will get olivine? It is because of fractional crystallization. If that place is the fraction of crystal that is formed separated from the magma, then you will get olivine. Then these are the rock types that will form down the series. These are the different rock. At the initial part, you will get ultramafic, ultraacidic rock. Then gradually they will convert to felsic rock. This is the solid line descent, you can say. And as the solid is forming from the melt, the melt is also evolved during crystallization. Then these are the things that changes down the series. You already know about it. That is, silica percentage will increase. Then stability will increase. So the olivine is least stable, quartz is more stable. Then down the series, MgFe percentage will decrease. SiO2 percentage will increase. Similarly, sodium potassium percentage will increase. Calcium percentage will decrease. These are the condition or changes that happen down the series of a Bowen section. So initially they will be mafic or basic. At the end stage they will convert to felsic. It will be less viscous, it will be more viscous. Another thing happen here, that is your doliomorphism. So doliomorphism occur in Bowen section series, which will produce a rock that is called a doliomorphic rock. This is your lamprophire. Example, so what is that? During reaction between olivine and silica. During reaction between olivine and silica, if there is a partial failure of the reaction, then some of the silica liquid will be remain. That is called as your released. That is not released thing. So when that will crystallize, that silica liquid is crystallized. That is called as your released mineral. So during partial crystallization, olivine is reacting with silica, there is partial failure. That means ki some of the silica is not reacting with the olivine. That means some of silica will get there. Kisira silica rahijibo ba balijibo as remnant. Some silica will remain. So gradually the liquid will enrich in silica, and the final crystallized product will be maybe a mixture of olivine, pyroxene, and quartz. So when it will happen? So that partial failure is a sudden cooling. Partial failure means what? Sudden cooling. So when olivine is reacting with silica, that is at higher temperature. Suppose 1000-degree temperature where silica will not crystallize. Okay. So during that reaction there is a partial failure. Partial failure means ki there is a failure in reaction, so that that temperature is not that temperature is decreased suddenly. So temperature suddenly decrease karla, but sudden cooling. Because of sudden cooling, now because of partial failure there is some silica left. Due to tomorrow sudden cooling, there will be olivine, pyroxene, and due to sudden cooling, quartz will also crystallize. So we will get a rock where these three will present. It is considered very unusual occurrence because olivine and quartz are never occur together because they have a very large difference in crystallization temperature. So that's why they will not found in a single rock. So this phenomenon is called as a doliomorphism, and the rock that shows it is called as a doliomorphic rock, which is explained in Bowen's reactions.